Okay, so to complete the proof of the existence of maximal tori in a reductive group, I have to prove the following technical theorem. So the assumption is A is a Noetherian local Hesselian ring. A prime is his completion. So since we are in the Noetherian case, we know that the map from A into its completion is faithfully flat. So let S be the spectrum of A. S prime is that of A prime. And so the assumption is let G be a fine flat S group scheme. Such okay, so okay, let S be the close point of S, and K be the residue field. And so the assumption about G is assume the special fiber is a K group of multiplicative type. Okay, so it is necessarily isotrivial because we have seen that over a field, every group of multiplicative type is isotrivial. And so we saw in August, we already saw in August the previous theorem is that there exists there exists a multiplicative, there exists an isotrivial group of multiplicative type H over S. So whose closed fiber is the given group of multiplicative type and an open and closed immersion from H prime, which is the base change to the completion of the local ring. Okay, and so okay, so this we proved already in August. So this was proved, I think, in lecture 10. And the new thing here, and so now the new result. That we are going to prove is that, so let's call it tau for tau prime, for instance. The new result is that tau prime descends to open and closed immersion down from H to G. So this is what we are going to prove. In fact, the statement that we are going to prove is that the natural map from the morphism of H group from H to G. So we are going to prove that this map is bijective. So the statement is that this map is bijective. Okay, so we know already. So let us call it theta for the moment. And so we have the two usual arrows going to from S double prime into H double prime, G double prime, where, as usual, the double prime is this. And we know already, we know that theta is injective. And the image of theta is a set of those U prime to H prime to G prime. Okay, and so we know that this map is injective, and the image consists of those group homomorphisms whose two pullbacks over S double prime coincide. Okay, so what we have to prove? So we want to prove that for every U prime actually, we want to prove that this is satisfied for any morphism. And since the family of subgroups, of torsion subgroups, is dense in H. Well, okay, so it is dense in H prime. It suffices. We can assume okay, so it's enough if we treat the case where our source group H is equal to its n torsion parts. Because if the result is proved in this case, this will mean that for any U prime, those two guys will coincide on the n torsion of H prime. And those groups are dense in H prime, and so they will coincide on the whole of H prime. So we can reduce to this case. Okay, so from now on, we make this assumption. No, because no, well, uh, note that, yeah, yeah, because everything comes from groups of S, and yeah, and so taking and we have this, uh, so we have this property. So it's enough to, so we can suppose that H, that in the first place, H is equal to its entorsion. Okay, and then H, which is equal to H, is a finite empty group over S. Since, okay, because so in the beginning, H corresponds to a finitely generated abelian group, and we take the entorsion, we mod out N in this finitely generated abelian group, and we are left with a finite group. So this is a finite group scheme over S. And okay, now we are going to use this. Okay, and so let Ng be the kernel of the map phi n from G to G, which sends G to Gn. So it's a closed subscheme. Because we have so it is a, because it is a fiber product. So we have G, which equals to G by this map. And here we have the unit section. Okay. And so even so is not abelian, and so phi n is not a group homomorphism. The so-called kernel is a closed subscheme. And of course, any um, any group homomorphism U prime from H to G factors through NG. Okay, and now there is a, let us make the following claim. So firstly, there exists an open enclosed subscheme Z of Ng, which is finite over S, and such that every S morphism from Y to GN with y finite over S factors through Z. So the claim is that there exists a largest finite subscheme of NG, and this is preserved by base change, that is Z prime, which is a base change of Z to Z prime as the same property of S prime, and thirdly, Z prime is an isotrivial empty group over S prime, and similarly, Z is an isotrivial group over S. Okay, so the proof of this claim is rather technical, and so we will finish with this. And so let us show that the result follows from this claim. Okay, so assume the claim. And let's U prime from H to G group homomorphism. Then firstly, as I said already, U prime factors through the n torsion, because we made the assumption that H is made of n torsion points, and H is finite over S. So by this property, hence U prime factors. Oops, sorry, I missed the prime here. Okay, and okay. So the assumption that H is equal to its n torsion, so it applies the same thing over S prime. And so we have this thing, and H prime is finite over S prime. Hmm? Yes, thank you. Yeah. And so by the claim 2, U prime factors through Z prime. Okay. And so now we have and so we have H prime to Z prime, but now both H prime Z prime are finite empty groups over S prime, and yes. Yeah. Both are groups of multiplicative type and isotrivial. Yeah, so the proof is you will see the proof of the claim is not easy. One first proves that there is such a closed subscheme exists. Then we prove that it is a group. Then it is a commutative group. And finally, it's a group of multiplicative type. Okay? And But we saw in August that the categories of finite, oops, yeah, yeah, they are also isotrivial. Okay, and we saw in August that the categories of finite isotrivial empty group of S prime. So this is the same as over spec. Okay, same over S. Okay, so since S and S prime are Enselian, yeah, they come from yeah, yeah, you're right. It's better from they come from and can be lifted to this. Okay, and this, so it comes from this and ends okay, so the end of the proof is something that we did already in August. So once we have reduced to the case of a morphism between two finite isotrivial groups of multiplicative type, we know that the morphism comes already from S, and so this equality is satisfied. So we only have to prove the claim, and the claim uses a couple of lemmas of proposition. So firstly, we have the following proposition. Yep. Yeah. Yes. Oh, yeah. You're right. That's a good question. I wanted to mention this because so you see here the technical difficulty is to descend something, some morphism from the completion of the Enselian local ring to the Enselian ring itself. But if we had gone through the proof of representability, then one could use Artin approximation theorem, which says that if you have a scheme of finite type over Z, say, well, so if you have some point in the completion of an Enselian ring, so you already have a point with value in the Enselian ring itself, and further you can well, and you can further impose restrictions on the okay, so if you can fix the values modulo any power of this. So here we only need the case. Okay, so we have something over K. It lives to a point with value in the completion, and we just have to know that there exists a point with value in the local ring itself. So if one has done the job of representability, then we can use Artin approximation, and so we don't have to bother about this thing. But I think it's interesting to see this proof, because this is how Grothendieck did it. So it was before Artin approximation. And so the proof is nice algebraic geometry. Okay, so the first proposition is so let S as before. So S local Henselian. So let me write as Noetherian to be safe. S its closed point. X to S scheme which is locally of finite type. And let's so assume we have a point X which is an isolated point in the fiber over S. And then the statement is that firstly, the local ring at X is finite over A. Yeah, A is so. Okay, so A is our Henselian ring. And further, if X is separated, let's say rated, then then is an open and closed subscheme of X. Okay, so I won't prove this, but so proof, I've written it in the note. So this is a, well, so this follows from a local version of the Zariski main theorem. Of the Zariski's main theorem. Okay, so let's assume this. Yeah, so this, well, so over a local Henselian ring, if you have a point in the closed fiber which is an isolated point, then this thing splits off the whole thing as an open and closed subscheme. And so we are going to use this okay, so now let us prove the claim. So our subscheme, the end torsion points in G is of finite type. And separated over S because G is well, G was affine and separated, and well, uh, um, well, G was also assumed to be smooth, so well, of a finite presentation. And um, okay, and what do we know? So over the close point, over the close point S of S, one has so if we take the fiber of this, and so this is a fiber product, so this commutes with base change. So this is the same thing as taking the fiber and the end torsion, but by assumption, G0 is this H0. No, that's not what I want to say. Hmm. Yeah, it could be, yeah. Yeah, sub-zero, sub-zero is the same as a sub, so these two are synonymous, but let me think, I'm just confused. Yes. Oh, I'm sorry. I forgot. Yeah. Sorry. Sorry. No, I forgot. Hypothesis. Well, I don't know if I. Well, is of multiplicative type. Well, maybe maybe I said it. I said it. Okay. And yeah. Okay. So I mean, so let's use a subscript 0 instead of, okay. And so, okay, so this is not the assumption, but no, the assumption is that this one is multiplicative type, and so this is finite over S, because so same argument as before. We have a group of multiplicative type, and so its end torsion is finite. Hmm? Yes. Yeah. No, because it's a fiber product, and so it commutes with. I think so. Yeah. Yes, but the kernel behaves well because it's a fiber product. So it commutes with base change. Okay, so we are going to use flatness later. So we have this, And so, and so, so we see that every point of NG lying over S is isolated in the fiber over S, and the proposition gives that our NG can be written as a disjoint union, something that we call Z, and something which we are going to denote with a star. And this one is finite over S, and this one lies above the open set S minus the close point. Okay, so this scheme splits, and so both are open. Okay, both are closed and open. And so we see from this, so we see that Z has the properties 1 and 2 of the claim. Okay, so it's in a sense it's the largest subscheme of this, which is finite over S. And so if we take okay, and so if we take a morphism like that, it has to factor through this Z, and and so one sees that if we go to the completion of the local ring, the reasoning is the same, and so we obtain that this is true. So now we have to prove that Z is a group, is a subgroup scheme. Is a subgroup scheme, that it is commutative. And finally, of multiplicative type. Okay. Yep. Hmm? Yes, 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 yes. So yes, yes, it is a completion. So they have the same closed fiber and also the same infinitesimal neighborhoods. Okay, so actually we are going to prove this over. We are going to prove the results for Z prime. Okay, so how do we do this? And so Z prime is finite over is finite over S prime, hence so is, let us call P prime, so that is and so let mu be the restriction to P prime of the multiplication of G prime, and also let tau be the automorphism of P prime, well, such that well, tau of Z1, Z2 is Z2, Z1. So it has the automorphism that switch the factors. Okay, and let Y prime be the image of P prime by the multiplication. And okay, okay, so what do we have here? So we have this P prime. So we have this multiplication map that goes into G prime. And so this is over S prime. So this is finite. And the hypothesis that we need here is that, so this is separated finite type. Well, and so by some results that I just so by some results in EGA 2, and so this is the part about finite morphisms. And so this is probably some afterthought about the same. So this says that well, so the image of mu is a closed subscheme. Is a closed subscheme of G prime, which moreover is proper over S prime. Yes. 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 Yes, this is exactly this. Yes. Yeah. Y prime is quasi-compact because it's the image of, so this is finite. Yes. Yeah. Yes. Yes, I think this is, yeah. Yeah, so we get that. So this is for the properness. So it is separated of a finite type, and the fibers are finite, and so it is proper. Uh, hmm? Mhm. Oh, yes, you're right. Oh, yeah. Mhm. Oh, yeah, you're right. I'm confused. Mm, mm, mhm. Yes. Mhm. Yes, you're right. Yes, you're right. If we use that, it factors through Z prime, then we are done. So maybe, yeah, okay, because I was about to prove that actually Y prime is equal to Z prime, but this seems to follow. Hmm. Okay, so yeah, so if we take this argument that it factors through Z prime, which seems to follow from the, yeah, from one and two. So we have that Z prime is a, okay, and okay, so mu factors Z prime, and so Z prime is a subscheme, as a closed subgroup scheme of G prime. And now we want to prove that it is commutative. Okay, for any integer m, so denote by a subscript m, the reduction modulo the, the power m plus one of the maximal ideal. Okay, so we want to prove that the group law is commutative. So we want to prove that mu coincide with mu twisted by the exchange of factors. And so let's K be the, well, I put, well, if I want to be, so the equalizer of those two things. So this is a closed subscheme of Z prime, because again, it's a fiber product. And it is finite. Well, maybe okay, so it is defined by some ideal I of that one. Well, so that prime is finite and affine over S, which itself is affine. So this is affine. Okay, but so what is that prime? So we add this thing here, and again the point is that this is a fiber product, and so taking the end torsion points commute with base change, and so we have this equality. So we have this, and so let me continue here. And so by assumption, G is flat over S, which is spectrum of A, and GM is flat over SM, which is the spectrum of A over this. And G0 is a finitely is some empty group of finite type over S0. Because so that was the starting assumption. And isotrivial because S0 is a spectrum of a field. And so this imply by something that we saw in August that GM is a empty group of finite type over SM. And okay, so here we use flatness and some result of well, some null result about well, groups of an infinitesimal scheme that reduces to empty group. So this one is of multiplicative type, and so this one is finite. So this is finite over. So this whole reduction is finite, and hence we see that the reduction ah okay, and so the reduction of so this one is a whole thing, and so this is the same as Km, because so when we reduce to this thing, so we have something which is commutative, and so they agree. Okay, and so this is and so this implies that um, and so the fact that Km is a whole thing after reduction modulo M, this means that the ideal I is contained in M plus 1 time for all M in N. Because this is commutative, because GM is of multiplicative type. Yeah, so the trick is that we don't know much about G, except that its closed fiber is of multiplicative type. And so this extends to the neighborhoods, infinitesimal neighborhoods of the closed fiber, and so that works. Okay. Yeah, yeah. I will give you an example. So basically, you take the normalizer for torus and you remove a point somewhere. Okay, so we have this for all M, and so we are in a Noetherian. So this is a so this is a Noetherian ring. Okay, and okay, and so this one is finite over A prime, and M-adically separated. And so R is a zero ideal, and so K is equal to Z prime, and so Z prime is commutative. Okay, so we are almost done. It remains to prove that it is of multiplicative type. Uh, mm-hmm. Yes. Okay, yes, but Ah, I see. Mhm. Oh, I'm confused. So what did I want to prove? Oh, yeah, okay. Um, okay, and so there is one more technical proposition that I'm not going to prove, but okay, so proposition. So we know that Z prime is flat over S prime because we saw that each reduction is flat over Sm, and each that so it is flat and commutative, and each reduction is multiplicative type. And so there is again some little work to do. So this implies that Z prime is a group of multiplicative type over S prime. Okay, so there is some extra work uh, to do. Okay, so let's assume this. So okay, now by faithfully flat descent from S prime to S, we obtain that Z is um, is an empty group over S. Okay, so well, actually the argument is the same. So I think that the multiplication map factors through Z, so it is a group, and a subgroup scheme, and by extension to S prime, it is of multiplicative type, and so it is of multiplicative. Okay, so this completes the proof of the result. Well, up to some technical part which I didn't. And so let me just give an example of a group G like this. So first, I start with the question. Okay, so we can take an algebraically closed field, and let S be the affine line over K, and take G the group SL2 over S, and so let's take the usual maximal torus. And so we can consider its normalizer. And so the quotient is a Weyl group with two elements. And so the question is, I don't know. So if we remove so I don't want to call this S, so let sigma. Okay, so sigma is the non-zero, the non-identity element in the back group. So if we remove sigma over the point 0 of A1, if we remove sigma from N of T, so we obtain a group scheme over group scheme H over H1, such that the fiber over the point 0 is equal to the torus itself. But I don't know. I don't know if this H is affine. Maybe it's obvious that it is or that it is not. I don't know. I didn't think about this. But the Mazur, but for sure the Mazur gave a slightly different construction. So in SGA 3, 19, considers considers the Lie algebra G over K of T such that so it's a version of SL2. Oh, and so if we make T equal to 0, so yeah, something like this. And it takes a GZ automorphism of G, and he proves that so he proves that each fiber is sorry, it's PGL2. If S is not the point 0, and the 0 fiber is solvable with 2 components. And he shows that if one removes the non-neutral component over 0, one obtains something which is affine. So we have an affine group scheme. And so let's call this group D like the Mazur. And if we consider the normalizer in D of a maximal torus, so it's closed in the former one, so it is affine. The fiber at 0 is the torus. And so this is an example of a group which is not a torus. Well, of course, we can replace this by the completion at 0. So we could take the ring of formal power series, and so we can arrange that the group is not is not a torus, but the closed fiber is a torus. But you see that the group cannot be much bigger than a torus. So in this case, it's a normalizer. Okay, so let me stop here. So, well, I will rework the proof, the written proof according to what we discussed during the lecture. So it seems that there is this shortcut that Z and Z prime are subgroups. And so this is it for this big theorem of the existence of maximal tori in reductive groups. And again, the proof is a bit long, but it's self-contained in the sense that it does not use the difficult representability theorem of Grothendieck, no algebraic spaces, and neither Artin approximation. Okay, and so the next lecture we will do some simpler things about, roots and root groups and so on. Okay.